Yeah, so good evening, both of you. I hope I am audible. Hello, am I audible?
Yes, ma'am.
Yeah, okay. So this is week six of
Yeah, we can head. Sorry.
problem
Yeah.
solving on fundamentals of electronic devices and materials. So last week Suraj had asked like a few doubts on questions in the previous assignment, right? So we'll start there and then we'll move on to like this week's content. So probably we'll first have a discussion on BGT and FET and MOSFETs. I think we'll discuss in the next class.
Okay.
Yeah. So
Okay, that's fine. But next class is the last one, right? Because that's going to be more on the photo substances,
no,
photoelectric
today
device.
like they have floated a Google form for the tutors asking whether they are willing to take one more session. So I have signed up for that. So on 21st we'll be having another session.
Okay, okay,
Yeah,
okay,
yeah,
okay. Okay, perfect. Makes sense.
yeah.
Yeah.
And the lights and
24th is the exam.
24th, I think. Yeah.
Yeah, yeah, yeah. Okay,
So
makes
yeah.
sense. Yeah.
Yeah, and one more thing is the LEDs or the light sensitive materials in those things, they're like a comparatively smaller portion. So even
Ah,
if we take some time for MOSFET, it won't make much of a difference.
okay, okay.
Yeah,
Makes sense. Yeah.
yeah.
That's fine. I think we can cover MOSFET also if possible because I've read that. I did
Okay.
not do the other part that is the photo electric
Yeah,
devices.
yeah, it's okay. Like I've planned accordingly. Like we can
Okay.
have a detailed session on BJT and FETs first.
Okay, perfect. Makes
Yeah,
sense. Then
yeah,
MOSFET we can do next week. Yeah.
yeah, yeah. So before that, let us discuss question number 9 you had asked from last week's assignment, right? Yeah.
Yes, I think those were not solved anywhere. I could not find any content or in the professor's solved questions, whatever. There also I could not find that. Okay,
Okay.
let's go and do that.
Okay. Yeah.
Was
So
it there anywhere? I missed it.
like actually a similar question is there, not the exactly same equation, but here they have asked the value of current value, right? We had solved on
Mm.
current density.
Correct. Current density equation is there.
Yeah, yeah,
Okay, let's go ahead and solve problem.
yeah. So
You want to project the question or you want to write it totally?
no, I'll write it. It's just
Okay, okay,
questions.
makes sense. Yeah.
So the voltage at which the reverse current in a germanium diode will reach 90 percentage of its saturation value is dash millivolts they have asked, and we have to calculate it at 300 Kelvin.
Correct. The voltage at which the reverse current is something with the reverse bias, right? That's what I
Your
understand.
voice is electronic. It's I don't know.
Now, can you hear me well?
Yeah, but it's kind of like watching the Transformers movie.
Okay. Let
Kind
me
of.
try to. Is it slow? I don't know. There is
No,
something.
it's like some electronic interference is there.
Okay. Let me put this away. Okay. I understood. Now,
Now too, it's kind of like that. Is it the same for you, Sarala, or
Yes, ma'am.
well, let me re-log in.
okay,
Okay.
fine, fine. Yeah. Hello, Sarala, am I audible?
Yes, ma'am.
Okay. I think I too will relog in if it's something from my end. Hello? Yeah, yeah, it's fine now. So, yes, yeah, like So the question here is, what is the voltage at which the reverse saturation current will 90 percentage of its saturation value? So if you remember in last week's assignment, we have solved something for J0 and J, right? So that is current density when you are talking in terms of J0 and JA. Suppose we are considering the same equation per unit area, you can convert that into current value. Yeah, so if you see the formula sheet, we know that J is equal to J0 exponential ED by KV into T minus 1, right? So there instead of J, we can just write I. Yeah. J is current density, current flowing per unit area. I is just the current value. We are not considering the area across which it is passing. But if you're considering, suppose you are considering a unit area, you can use the same equation for J and I, right? Yeah. So whatever it's there in the formula sheet is for J, same equation you can use for I. And I think in the formula sheet there is one small issue that EV minus one part is missing. Like if you see the equation for J is equal to, yeah, minus one should be there, right? Yeah, that part is not there. So here, instead of using J, we will use I is equal to ISO or I0 exponential of EV by KB into T minus 1. Yes, for the current value. Yeah, and no, like they'll ask specifically. Here they have asked for the reverse saturation current, right? Or if you they want you to determine in terms of J0, they'll say current density. Yeah. Here it's just current, so it's the same equation, only the terminology is different. Yeah. And here the voltage at which reverse saturation current will reach 90 percentage of saturation value. So ISO is the saturation value, right? This is the saturation value, saturation current density. Yeah, from yeah. So they have asked it becomes 90 percentage of this value. So I becomes 90 by 100 of ISO. And since it is reverse saturation current, there should be a negative sign here. So we'll substitute for this particular I value, then we'll substitute minus 0.9 ISO is equal to ISO e power EV by KB into T minus 1. Minus 1. And this I0 will get cancelled and you can find the value V. Hello? Yeah. Can you just try that? Yeah. 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 Since it is in the reverse bias, they are asking the reverse current, right? So that is the reverse biased one. So we have to put a minus sign. And if the question was in forward bias, we will put a plus sign, 0.9. Yeah. So if you solve this, you will get the value. Can you just try that? Yeah. Yes. Like they have asked the voltage at which the reverse current in a GE diode will reach 90 percentage of its saturation value. This is 90 percentage of saturation value. I becomes 90 percentage of ISO. Yeah. -0.9 is equal to e power e. Yeah, you can like put ln on both sides, and ln of -0.9 will be sorry. Okay. Yeah. Yeah. Sure. 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 Yeah. Sure. So it will be 1 minus 0.9. 1 minus 0.9 will be e power e by kBt. So 0.1. No, no, like this one we have to bring this side, right? Yeah. Sorry? Yeah. Yeah. E by kBt. Yeah. Now we have to find V. 1.3 into 300 is equal to 1.6 into 10. Yeah. Okay. And minus 0.05. Yeah. So approximately minus 60 millivolts, right? Yeah. So there is option like minus 60 in the A, like the fourth option. So that will be our answer. J is current density, I is current. It's the same concept, everything is same except for the J and I, whatever we substitute. Otherwise, everything is same. Yep, area. Yeah, we are like the final answer we are saying logically will be like this much current is flowing per unit area. Otherwise, we are telling that this much current is flowing irrespective of whatever the area is when they are asking current. Yeah, yeah. In the like 10th question, they have asked calculate voltage across an SI diode if 90 percentage of reverse saturation current is flowing in forward bias. Yeah, forward bias at 300 Kelvin. Yeah, so can you calculate like without me interfering in anything? Can you just calculate? Yeah. Yes, yes, same equation. Yes, 90 of S naught instead of minus 90. Yeah. It's 90 percentage. Okay. Yeah. Yes. Yeah. Okay. Now you have to convert it into millivolts. Is it 0.16 or 16.6? Yeah. 6, yeah. So 16.6 millivolts is the answer. Same equation, only thing is that like yeah, yeah. So that's all. Yeah, now had asked about the question number 14. So yeah, yeah, sure. Yeah. Subjected for n to is equal to 300 Kelvin. Ni is 10 power 10 centimeter Amps. So this is the question. So there is a silicon PN junction. Na and Nd is given, that is the holes and electrons on the acceptor and donor sides. And they have asked that at an external forward bias of 0.4 volt, how many carriers are injected from N to P? Temperature and Ni is also given. Yeah. So so if you see the equation sheet, you'll be able to be like there is a direct equation there. Can you just check your equation sheet? Let me come up which line it is. Like just after PN junction depletion width they have given. Yeah, minority carrier injection and PN junction is given, right? Yeah, yeah. So this is the equation that we have to use here. So like you won't be able to connect like minority carrier injection, right? So if you read carefully, so this is your PN junction part. You have the P side, you have the N side. So the P side they say that there is 10 power 15, and the N side they say that it is 10 power 16. And it is in forward bias. Forward bias meaning that N will be connected to positive. So because of this, what happens? Whatever electrons are there, it will be forced to move to the P side, right? And when it reaches the P sides, they become the minority carriers. So this is actually minority carrier injection. Yeah, yeah, yeah. So if you see that minority carrier injection, we can directly calculate using that equation. N in P side is equal to N in N side exponential of V0 minus V external by KBT. And for that, initially you have to calculate V0 is KBT by E ln N and NP by Ni square. And just, yeah, Na and Nd, yes, yeah. Yeah, so first we have to find V0, then using that V0, you have to substitute in that NN equation. So can you just try? That is the at an external forward bias 0.4 volt. Yeah, yeah, yeah. Can you just try? Yeah, but still, can you just so that you get the answer? Have you got the V0 value? Yeah, yeah, 0.655 ohms. Yeah, at an external forward bias of so and so, how many carriers are injected from N to P? To P. Yeah. Yes. 16. 16. Sorry, virtual calculator. Yeah, you, I think you press X first and then put E. Or if you know the value of U, you can use X power Y. Like, okay, okay. So is this how your substitution looks? 10 power 16, then exponential of a very, yeah, uh, minus 1.6 into 10 power minus 19 into 0.655 minus zero point 0.4, yeah, by 1.38 into 10 power minus 3 into 300. Like, what was the equation that we had to use? Yeah, Okay, let me check. Yeah. Okay, so I think the voltage part we are converting. So let me check once again. So the voltage is in. Okay, yeah, this is not there. Yeah, true. Yeah, yeah. Okay, okay. So okay, okay, fine. Yeah, like you understood the substitution, right? Okay, fine. Yeah, yeah. So any other doubts from assignment 5 or any previous assignments? Okay. Like only thing is minor whenever they are asking a similar question like from where it is injected to where, like try to visualize it and see if it is minority or majority. Yeah, moving to the yes, yes, yeah. No, you can just change that equation, and then the question will be like reworded accordingly. Yeah, yeah. But minority carriers will flow like in that case this forward bias they'll change to reverse bias. Yeah, yeah. So then the same equation you can use. Huh? Mhm. P side, yeah. Yeah. But in that case, we won't call it as a phenomenon of minority carrier injection. It won't be called as such. Like this kind of phenomenon happens only when there is an external forward bias, and because of that forward bias, the electrons from here are getting injected to the P side, right? Yeah, yeah, yeah. Okay, in the same setup you are asking. Okay, then that is possible. Yeah, yeah, it's possible. Yeah, yeah, that too you can calculate. Yeah, yeah, you can calculate. Then that the n naught p instead of it will start as n naught 0 is equal to n p 0 exponential. Yeah, yeah, just the carry na and nd will be like yeah, that's it. Rest all will remain same. Yeah, in the same setup, in the same setup. Yes, yeah. I thought you were asking about reverse bias. Okay. Yes. Yes. Yeah. I is not. And that you have to like even if it is J or I, only the wordings will be different. You have to substitute the use the exact same equation. Yeah. Like in last class we had solved in current density and in the assignment it was just mentioned as current. Yeah. Only that was there. Yeah. So I think we can now move on to transistors. Yeah. So I think till week 5 we were talking only about PN junction diodes and two terminal devices, right? So when moving to transistors, can you tell me it has how many terminals and how many junctions? Yeah, so three terminals and two junctions. And a predecessor to this, like to the transistor, can you think of? Like before the before the solid state transistor came up, what was used before this? A same three terminal device, but the name is different. Yeah, triode. Yeah, or commonly known as the vacuum tube. Yeah, vacuum tube or diode. So whatever we are going to see next, that is the BJTs or the FETs or the MOSFETs, everything will be three terminals and two junctions. Meaning that in the same thing, like the material would be divided such that there are two depletion regions within it. Yeah. So that is transistors. So I think as part of your syllabus, first what you like in the lectures, first what they discuss is the BJT. BJT. That is bipolar junction transistor. So basically, it consists of three differently doped regions. So, like, can you tell me, like, when you have, suppose this material has like three doped regions, two are P, one is N, and if among these two P's, one is more doped, how would you denote that? Yeah, yeah. So in BJT, like, what happens is that it is a like, three cases of doping, and in that configuration, it can be either PNP or NPN, or it can be such that this P or N can have an excess doping. So then it will be P plus NP, or say N plus PN. So it consists of three differently doped regions and can have a configuration of NPN or PNP, whatever it might be. And one more thing is it has three different regions based on their functions. Okay, if you recall, it would be an emitter, base, and collector. Collector. This is emitter, base, and collector. So, what do you know about the doping of an emitter? Like, how will it be doped? This, yeah, yeah, like moderately doped, you can say. So, then if you check, like, suppose you have a PNP transistor, this is your P plus NP. And now, if so, this is the emitter, this is the base, this is the collector. So this particular between the emitter and base, how would the depletion region lie? Like we have said that the emitter is heavily doped, right? Yes, would be more in B, less in emitter. But in the other case, it would be like equally distributed, right? More or less equal. Yeah. So, and I think for BJTs and FETs, usually you get only like maybe logical questions. It won't be much of like numerical questions, I think. Yeah, but for MOSFETs, I think you may get numerical problems as well. Yeah. You know, or you can ask, let's see. Okay, fine. And one more thing is we can use these BJTs in three configurations. It can be common base, common collector, or common emitter. Yeah, so depending on like which is the common, and one more thing with these transistors is that in all types of these devices, what we do is that we will vary the voltage or current across two terminals and take the output that can also be voltage or current across the other two terminals, right? And in case of BJTs, it is a current control device. Yeah. So any doubt in this part? Yeah. Means yeah, that depends on application, I would say. Yeah, like why do we use a common base, common emitter, or common collector? Depend on like which output and input we want, like what input we want to vary and what output we want to get. Yeah. So and now let us take the case of a P N P BJT, and it's like you understand how to draw the diagram, right? Yeah. Okay. So this is your emitter, this is your base, this is your collector. Yeah. And now the emitter base will give it in forward bias. So this is P and P. This is P. This is P plus actually. P plus. This is N, and this is again P. So this is in forward bias, and this part we are giving a negative bias, reverse bias. Okay. Yeah. Now what do they say? Transistors. So, and there are three currents associated. This is the IE part, this is the collector current, and this is the IB part. Means, okay, yeah, yeah, holes, yeah, B, yeah. Some amount of recombination will take place. That constitutes IB. Yeah, yeah. Basically, and remaining of what passes through this. So we have the again it goes to the P region, right? And like the thing is initially when you have this is in the forward bias, there is holes here. The holes will be forced to move across IB. Few of them recombine. Again, they reach the P part in the NP, like P plus NP. From P plus, it initially goes to the N part, which is the base. Few of the recombinations happen there. The remaining goes to P, right? Even though holes, yeah, yeah. Suppose this is P plus, this is N, this is P. So initially there are holes here. They move because of the forward bias, they move on to the base region, which is N. Some amount of recombination happens there, it constitutes ID. The remaining holes go to the P region. And even though there are holes are the majority carriers, there too there is minority carriers, right? And here if you see the holes, it is connected to the negative terminal. Negative field, and because of that the holes will recombine with the electrons and are pulled out of the circuit. Yeah, that is what constitute IC. Yeah, no, that is what you should remember, like out of this IB, IC, I three are there, right? IB, yeah, and that not necessarily like that is what we supply. We are supplying across two terminals and measuring across two terminals, right? Yeah, depending on what you want, you can supply across E or B. Yeah, yeah. So that is the IE, so which you are supplying IE and you're collecting IB and IC. This external bias. Yeah. This one. No, depending on how much we vary this, these values will change, right? Yeah. 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 Yes. Yes. Yeah. Yeah. Huh? Yeah. Huh? Moving around. Yes. No, like this equation that they're saying, it's not like an explicit equation. It is like theoretically, IE should be equal to the like sum of IB and IC. And this IE, yeah, yeah, yeah. That is the current transfer ratio. Yeah, yeah. IC by IE. Yeah, Mm, okay. If you're like, if you want to call it that, okay. Like, what are you coming to? Mm-hmm. This is adding value. It is constant. Like, though the amount is small, it is contributing to IB. Means you are asking in terms of the equation, like IB is not just the alpha value matters. Is that what you're asking? Yeah, yeah, yeah. Then only alpha matters. IB part. Yeah, yeah, yeah. Like in ideal case, IB should be zero, but since it is a non-ideal condition, some amount is lost as IB. Like IB, you can like logically equate to the loss that is happening because of the unwanted recombination. Yeah, yeah. So that is the BJT in common base configuration. Similarly, you can go for a common emitter configuration. So what happens is that instead of like this forward bias and reverse bias, whatever you are applying, it will be across the here instead of the base, it will be the emitter, and whatever you are supplying will be across the base and collector. Yeah, that's the only difference. And in the common emitter config, huh? So there the emitter base will be forward biased and base current will be the input current and collector current is the output current. Yeah, yeah, it's in common base we are giving E and taking out V and like IE we are giving and we are taking out IB and IC, right? Yeah, there what we are doing is that IB is what we are giving in and we are taking out IC. Same thing, like recombination losses. Yeah, and one more thing to remember is the common emitter configuration is the configuration in which it acts as an amplifier. Because IB will be a very small value and it will be amplified when it reaches the IC. So in the whatever amplifier configuration we use in BJT, it will be in common emitter configuration. Yeah, yeah, amplifier. Yes, yeah. Common collector, I think it would be like whatever we want. It's not like we can say it's in an amplifier or anything. Like it would depend on our need. Yeah. So that is all about BJT. Yeah. So, and from transistors, like, can you tell me a logical answer? Which of the following is not a function of transistor? So, I'll give you the options. So, first one is it acts as an amplifier. Then it acts as a rectifier. Okay. Then it can modulate power. Okay. And finally, it can allow current to pass through two terminals depending on voltage across another terminal. Yes. Voltage across other two terminals. So only answer is not a function of transistors, it acts as a rectifier. Yeah. It can modulate power. Yeah, it can modulate power. Yeah. So transistor can yeah, I into V. IV characteristics. Yeah. Yeah. So I think transistor and BJT part is clear, right? Yeah. FET. So FET like BJT actually what they do is that they while like depositing the like semiconductor itself, these regions will be differentiated, right? Like you have a P material, you have an N material, you have a P material, they'll be sandwiched and treated and so on. But FET is the name field effect transistor. There are no distinct junction. What happens is that it's actually, suppose you have an N material, and on top of that N material, you superimpose a P material either by diffusion or some external process like that. So that is what happens in this JFETs. Here, though, what we do is that distinct regions are there, but here, yeah, like manufacturing wise, that is the difference. Yeah. And in case of a BJT, these distinctions between emitter, base, collector, and so on so can exist even in the absence when we are not providing any external field or anything. But in FET, suppose these like you're superimposing this P part on N or whatever it is, right? If you're not doing an external process, this particular like, external region won't exist. Yeah. So manufacturing wise, if comes a question like what is, and like we are a descriptive question like how can you differentiate between BJTs and JFETs based on their manufacturing, you can say that in case of BJTs there are distinct regions in the absence of an external field, but that is not the case for a JFET. Yeah. And in case of JFETs, current flow takes place through a dash in the device. What is this portion called? Channel. Yeah. Channel. It is a channel based device. Yeah. And depending on the external bias we are using, we can either pinch off this channel or we can increase the width, decrease the width, and so on. Right. So in like suppose you are applying too much of a voltage, sometimes pinch off happens and the channel will be lost. Right. Yeah. Bus bias. Yeah. Yeah. I can come to that. So let me first draw. So in case of JFET, there is the source, there is the gate, there is the drain. Right. And the source and drain, they are connected by the channel. And this channel is the pathway for carrier transport. Whatever carriers we have, it is the pathway for carrier transport. And whatever bias that is, so and this gate is there, right? The bias of the gate decides the, that is the bias in this, what is the sign and what is the value. The gate bias determines the channel width and the resistance offer. It determines the channel width and resistance offered. Yeah, this much is the basic. Like what is an FET? Yeah. So now let us draw a JFET. Simple. Let me. So this will be the one that I'm using. That this you have an N material. That this is the source. This is the drain D, and here you have one part of the gate and you have another part of the gate, that is the P region. So this is P plus, this is also P plus, both are heavily doped, and because of this junction we have two depletion regions, right? And most of the depletion region will lie in the N part because it is heavily doped. So this is without any external bias. And now first case we'll like how pinch off happens, we'll first is like assess when in terms of there is that voltage between G and S, that is gate and source, will be zero, that is they will be shorted with each other. And so let this short this two part, and the drain part will be positively biased with respect to the source. Drain positively biased with respect to source, which means how would this translate to in terms of voltage? There would be a flow of carriers, right, from S to D. Yeah. and therefore there will be pull from D, because of which the carriers flow from S to D, right? Yeah, yeah. So electrons will flow from force to D. Then now you wanted me to tell you like what happens with increase in this voltage, or is that it? Like, oh, okay. So let me then bias this. Okay, this is negative, this is positive. Okay. Yeah. So what happens is initially VDS is greater than 0, right? So when VDS increases, what happens is that current flow increases in the channel. But here what happens is that this part of the channel, right, it starts to narrow. Like this part of the channel, it starts to narrow. Yeah. Yeah. More electrons will flow, right? Yeah. I'm not understanding like what is your doubt here? Like okay, yeah. Yeah. Okay. So depletion bit part is clear to you. You want to know like why the N channel? See, like okay. Yeah, but the depletion region, if you say like depletion region essentially mean that there is no charge carriers in that area, right? Nothing is moving in that area, everything is arrested. Depletion region. So if when the bulk of electrons starts moving from S to D, there the concept of depletion region starts losing its value. Like there are excessive charge carriers flowing towards this part, right? That is why we say that towards this ends, the depletion region starts narrowing. That region gets filled with carriers. There is no distinction like, yeah, that region is empty. It becomes a continuous place. And that is why we say that the current flow becomes a constant value. Yes, yes. Yeah, pinch off doesn't means that the flow is stopping. It means that, yeah, yeah, because that image I feel is kind of misleading. Like they just show this portion to be cut off like this. So we would think that okay, nothing flows beyond this. Yeah, yeah. It's not like that. It's like because of like this too much of electrons moving from S to D, the concept of an area where there are no like carriers, yeah, that is not there. It becomes a constant. Yeah. No, 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 no. It's just that the current becomes constant. Yeah, so that is why when we draw the VI characteristics, what happens is that initially, if you see with the increase in voltage, it was increasing, but beyond the point, it just goes like this. Yeah, and this particular voltage is the VDS is equal to VP, that is the pinch off voltage. Yeah, yeah, that is the case. Yeah, any other doubt from that part? Yeah, okay. Like you're asking like what happens suppose instead of shorting this gate and source you're applying a potential there, gate and source. Yeah, Yeah. That is between S and D, everything remains the same, but between the S and G, we are applying a potential. Potential. Okay, there too, what happens is that the depletion width goes on decreasing. Yeah. Hmm. Suppose this VGS what we have, right? If it is, yeah. I'll draw that. So this is the case. And to have this here. Here, this is the N part. Okay. This is the P plus parts. And then this is your S, G, D. Between S and G, now we have this. Yeah. Yeah, reverse is the thing. What is explained there is reverse, I think. No, I think based on what, like what was explained in class, it is this thing. Like S N is connected to positive and the reverse bias is applied across this thing. Yeah. And here the same goes the same. Yeah. 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 And when this value that is VGS is greater than 0, then the width will increase. Channel width will increase. Yeah. And if this VGS is less than 0, what happens is that width will get reduced. Like initially itself, the width will get reduced and therefore pinch off will happen much earlier. Width will decrease. So this, yeah. So the width will decrease means that already it has been like increased to this part. And now what happens is that because of this excess flow, it gets pinched off much earlier. Yeah, the VP, the pinch off voltage in this case will be much lesser. So if you go to this curve, what happens is that here this was the P required for pinch off to happen. And now what happens is that it pinches off much earlier. So this is VGS is equal to 0. That is when the G and S are shorted. This is VGS less than 0. And suppose you are going for like higher VGS value greater than 0, pinch off will happen later. It will go to a, yeah, 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 yeah. That is VGS greater than 0. Yeah. So we look at a few questions like theory based questions for this. Okay. MOSFET like we'll take the next like two it's yeah. Okay, or you can do one thing like the question numbers you can send to me and I can reply to you. And last time I saw your mail a bit late. Yeah. And 6003 This is my number. Like if you want, you can after sending the mail, you can just ping me so that I'll notice that faster. Yeah. 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 It is 6303 228 660. Yeah, last time I like I saw your yeah much late, so I thought like and once you send the mail and that goes for both of you. Like if you have any doubts with the assignments, please take a snapshot of that question and post it to me and just ping me in WhatsApp. Yeah. Okay. So anything else with JFETs? It's clear. I think that's all about JFETs and things, right? So if that is the case, then maybe we can wind up today if you don't have any further doubts. Or you can do one thing, like the questions regarding the MOS, like whatever doubts you have in the assignments, you can ask now and they can give you hints. Like you can try with that. Even if it doesn't work out, then you can mail me. Okay. Okay. Okay, fine. Yeah, sure. Okay. Choose the options with respect to oxide layer MOSFET. Cell thickness. Okay. 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 Based on the question, choose which of the option. Okay, the oxide layer acts as an inductor. So the MOSFET as a whole acts as the inductor, right? So the oxide exclusively, if you think about the oxide layer, will it? Hmm. Hmm. Yeah, but no, like suppose they are asking like with respect to an oxide layer and MOSFET. In ideal case, if you are thinking, will that be? Yeah, yeah. So then that's it. Yeah. No, no. Yeah, only A and C are correct. Yeah. Yeah. Then any other question? Valid comparison between BJT and JFET. Have you tried that? Question 3. Okay. Okay. Yes, yeah. 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 Flow, yeah. BJT both can flow. Yes. Yeah. Electrons, yeah. It's unipolar, yeah. No, no, only for JFET, yeah. Okay, yeah. Yeah. So B and D. Yeah. Yeah. So transfer the system. Confortation to another pair of terminals, yes. Sixth one, yeah. Then very strong inversion. You have to check for the condition at strong inversion. What is the relation between phi S and phi D at strong inversion? That is the hint. Yeah. Yeah, that is the hint. Yeah. Okay. Yeah. Correct, yeah. So 1, 3, and 4. Okay, yeah. Option from D, yeah. Should I do it now or once the submission is done? Yeah, I don't want to get into trouble. Yeah. P, so, okay. Source, yeah. P, yeah. 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 There is same. Yes, and yeah. Now it's a problem again. Intrinsic. Yeah. Intrinsic means that they would want us to find is it 5B, 5S, what can you? Yeah, 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 yeah. Emitter will like always be heavily. Yeah, yeah, yeah. Then again a problem. Strong inversion, same case. Yeah, 5B 2 times 5S. Sorry, 5S 2 times 5B. Then okay, here they have the condition of strong inversion. And finally, they want us to calculate the hole and electron concentrations, right? So PS and NS, okay, Ni square by PS we can do. PS will have to use the equation which involves 5B. Formula sheet, let me check. Okay, probably I think devices part is not. Okay, let me talk to sir in case there is a possibility of including it. I'll just ask sir. Okay. No, that we all, it's not there here. Yeah. Okay. So let me ask sir, like whether they can include for this part. Yeah. Do you want equation for 5D to be added? Then equation for PS to be added, right? These two. Okay. Let me talk to sir. Yeah. Okay. Fine. Fine. Yeah. You can mail to me and then just ping me. Yeah. 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 Sure. Mm. Yeah. Sure. Anything else you want to? Yeah, theory on MOSFETs, and we'll go into the LED laser and all those things. And in final week, let us, yeah, we can solve. Yeah, step by step we can solve these. And first we'll go through an overview of MOSFETs, then step by step we'll solve this, and then we'll move on to the whatever content is there from week 7. And finally, yeah. No, the officially it is the last. I have signed up for taking another session on 21st as well. So I think in general you should be getting like at least two or like on an average 3 sessions more. Like that will be the thing. At least two will be there. Yeah. Yeah, I think like problems will be there. Yeah, yeah. Okay. Yeah. Thank you so much for joining, both of you. Yeah. Thank you. Bye. Yeah, sure. No problem.